Hello, this is video 10 already, and even though I accidentally erased it, we are still kind of talking about number systems. What we haven't done is answer the question, why do we even need to look at number systems? And rather than just lay out the answer, I'm going to kind of sneak up on it. Maybe we will figure out as we look at some additional stuff why it's actually handy. I'm going to do that with a number system table. I'm going to try to write small enough to fit it on the board and still large enough that you could read. I hope you could read it. You might have to increase the size of your screen. But let's put them side by side. We first talked about decimal, did we not? Decimal. And then we talked about binary, did we not? Binary. That says binary. It doesn't say binary. And we talked about hexadecimal. And already I can tell this is going to be ridiculously difficult for me to keep the columns, the rows straight, the columns lined up, but I'm going to cheat and use a different color to underline it like it's lines on note paper. You don't have to do anything like that. This is for my benefit. 0. Okay, let's all count together in the number system that we like. 0, 1, 2, 3, and I'm going to already need to draw a line there. I'm going to draw a line. That's just for my benefit, just so I can try to keep the rows lined up. 0, 1, 2, 3, 4, 5, 6, 7. Another line. Eight. See how easy this is? Decimal? 8, 9, 10, 11. Line. 12, 13, 14, 15, line. 16, 17, 18, 19, line. I got one more chunk I got space for. 20, 21, 22, 23. And no, that's not all the possible decimal numbers. That's just all I could fit in this column on the whiteboard. For review, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 23. Okay? I don't need the blue anymore. Got some lines. Binary. Well, 0 is 0 in any number system. So binary 0. Now, here's a strange convention. Convention means it's not a hard and fast rule. We just all agree to do it that way because that way we can understand each other better. We in the biz, when we're writing binary numbers, will almost always write those as chunks of 4 bits. It seems like it's a silly thing to do, but remember we can't access individual bits in the computer anyway. 4 bits is half of a byte, so 8 bits is an entire byte. That's the smallest chunk of memory we could pull into a register anyway. So I'm going to write this as 0, 0, 0, 0 and hope that that explanation was sufficient. Binary 0, that's still plain old 0. That's nothing but zeros on the place value chart, and they all add up to 0, so there's still no problem. The 1, I would write that as 0, 0, 0, 1. The 2 doesn't look like a 2. We don't have a 2. We have a 1 in the 2's column. If you've taken notes on the videos up to this point, at this point you might want to refer back to that binary number chart, and you will quickly realize that a 2 in binary looks like 0, 0, 1, 0. On the place value chart, the one and only 1 will be in 2's place, so that's the only one that contributes any magnitude to the number. What about 3? Well, it looks like an 11 because that's a 1 in 2's place and a 1 in 1's place. 4, we have to go over to the next place value. 0, 1, 0, 0. 0, 1, 0, 1 is 5. 0, 1, 1, 0. That's a 4 and a 2 equals 6. And 0, 1, 1, 1. That's a 7. Look at this trick I can do. Oh no, I don't want to have to add up all those ones and find out what they are. Well, that's the largest number I could represent in 3 bits, which is 1 less than this number. A 1 in 8's place on the place value chart. 8 minus 1 is 7. See how cool that works out? Okay, 9 is 1, 0, 0, 1. 10 is 1, 0, 1, 0. 11 is 1, 1. No, it isn't. 1, 0, 1, 1. 8, 9, 10, 11 on the place value chart. I fixed it. 12 looks like 1, 1, 0, 0. 13 is 1, 1, 0, 1. 14 is 1, 1, 1, 0. And 15 is 1, 1, 1, 1. Whoops. I ran out of space. I need more bits to represent 16. Well, it turns out if I add bits, I go ahead, by this convention of always writing binary numbers as chunks of 4 bits, I'm going to actually add 4 more bits instead of just 1 more bit here. So when I do that, that'll give me a place to put the 1 in 16th place with 4 zeros after it, but I'll have 3 leading zeros. There we are. Look at that. That is a whole byte there. That's a mouthful. 1 whole byte that equals 16. 0, 0, 0, 1 in 16th place all by itself, and zeros in 8, 4, 2, and 1's place. 17, 0, 0, 0, 1, 0, 0, 0, 1, a 16 plus a 1. 18, 0, 0, 0, 1, 0, 0, 1, 0. 16 plus 2 on the place value chart. 19, 0, 0, 0, 1, 0, 0, 1, 1. 16 plus 3 more. 20 will be 0, 0, 0, 1. These are getting messier the further down they get on the board, aren't they? 0, 0, 0, 1, 0, 1, 0, 0. 21, 0, 0, 0, 1, 0, 1, 0, 1. 0, 0, 0, 1, 0, 1, 1, 0. And finally, mercifully, down at the bottom, 0, 0, 0, 1, 0, 1, 1, 1. That will be 16. If we put this on a place value chart, 16 plus 4 plus 2 plus 1. 16 plus 7, also known as 23. We did it. Okay, make way for the monster. You know what? I'm going to move hexadecimal over. Make it closer. Trying to cozy up to binary over here. Hexadecimal. It gets a long way. It gets a lot of mileage out of just single digits, huh? 0, 1, 2, 3. Starts out plain and simple and gentle enough. 4, 5, 6, 7, 8, 9, 10. Oh. It doesn't look like a 10. I made a boo-boo. We've got to be able to represent every number less than the name of the base down here with a single digit. That's when we pulled in the reinforcements and got A, B, C, D, E, F. We're still in single digit land all the way down this chart. Now, when we add 1 to F, it flips over and to represent 16, we'll need a 1 followed by a 0. On our place value chart, that will be a 1 in 16's place plus 0 added to it, which is 16. 17 looks like an 11, but we would read that as 1, 1 base 16. Don't even call it an 11. It's not an 11 anymore. It's 17. 1, 1 base 16. 1, 2. 1, 3. 1, 4. 1, 5. 1, 6. 1, 7. ... Still, with this huge long table, we stare at it, and we still ask, why? Let me see if I can try to figure out why. There are how many 1s show up in the hexadecimal column here? There's one of them. I spy, there's another. There's 2. Oh, there's a whole bunch of 1s down here. I'm going to circle them. Not that, that's the color for these sides. I'm going to circle it with green if the green shows up. I spy a 1 in the hexadecimal column. I spy another 1 way down here. Look, I spy 2 of them and a single number there. A couple more 1s. And I could circle all those, but I'll leave that as an exercise. You can circle those 1s down there. Now, that was so much fun. Let's do that again, except this time, in binary, let's circle all the patterns of 0001 that we can find. I found one right here, 0001. Any of these? Almost, but that one's backwards. Oh, here's one, 0001. Here's two in a row. Here's another. Look at this. Every place I circled a 1 in the hexadecimal column, I circled a chunk of 0001 over here in the binary column. Ladies and gentlemen, that's why we are not wasting our time to look at and try to understand hexadecimal. Hexadecimal is, for humans, it's a concession to meat-based processors. It's hard for us to read large binary numbers. It's actually hard to read hexadecimal. But this, hexadecimal, is shorthand for binary. The hexadecimal number system. Here's how we would talk about it in mathematical terms. There is a 1-to-1 correspondence between every possible pattern of 4 bits and every possible single hexadecimal number. Look at this. Decimal is the outlier. Decimal flipped over and started using more than one digit right here. Where did this flip over and start using more than one chunk of 4 bits? Right here. Where did this flip over and start using more than one hexadecimal digit? Right here. Perfectly matched up with binary. If we kept this going, if we had a huge, ginormous whiteboard and all day to fill it in, then everywhere we saw a 6, over here in hexadecimal, let's try it. 6 is this bit pattern, 0110. Do I spy a 6 anywhere else? Here's a 6, look at this, 0110. There it is. You can convert between hexadecimal and binary. Here's the fun part, here's the good part, the easy part. We can convert between these two number systems without even having any clue what the number actually is. We just replace every chunk of 4 bits with the matching hexadecimal digit. If we're trying to go from hexadecimal back to binary, we take whatever the hexadecimal digit is and replace it with its 4-bit pattern. It's amazing. It's miraculous. And even better than those two things, it is easy. I'll try to prove it in the next video. I'll see you online. Something to look forward to. I got to end with, I'll see you online.